Hi, my name is Shad, and I'm going to be your teacher and guide today for this course on software reverse engineering. So that's the technique of taking code that's already been compiled and reversing it into something that you can manipulate. So that means you might see the source code, or at least you will be able to see the assembly language and then make any modifications or understanding of what the program is doing. So this course is taught in 8 pieces. In part 1, we'll talk about numbering systems. So if you have not seen binary numbers or hexadecimal before, this will give you a great start into how you can understand what a reversed piece of software looks like. Then we'll do some experiences to get you used to the idea of software reverse engineering, the first attempts. Then we'll have a session where we compare the different tools that are popularly available. And of course, we're looking for free tools, but there are commercial ones as well. And then we'll talk about the reading the stack feature. So this is understanding a program as it's running and doing some debugging while it's in action. Binary patching is about taking a piece of software and modifying it, even if you don't have the source code. And so you can patch things to fix errors or to maybe bypass a certain feature like a login screen or a registration screen. Recognizing code patterns will give you a more in-depth advanced feature of how you can see maybe malware and diagnose what it's doing. And then anti-debugging techniques is the ability to take a piece of software who is trying to hide from you. So this is a cybersecurity topic where we are looking at software that knows that you are reverse engineering it and you're trying to avoid that. And then finally, we'll do some fuzzing techniques. And that's this video here right now. So this whole course here is about software reverse engineering. Now, the guides that are going to take us through here are from Dakota State University. So Michael Ham and Andrew Kramer are both the teachers. So let's get started with this section right now on software reverse engineering.
So my plan for this last hour is to do some fuzzing. And I thought it would be fun. We can do this together. I have a piece of software that you can download and fuzz on your own that I know for a fact has an exploitable crash that you should be able to find. But the same techniques that I'm going to show you here apply pretty directly and easily to other pieces of software. It should be easy to take what I'm going to show you and just fuzz GDB with it, or fuzz any of the GNU tools that you can download and build and run. So let's talk about fuzzing. And forgive me just a moment as I get this going. Yes. Okay. So I'm going to make it my goal to talk for no more than like 10-15 minutes about the theory of what we're trying to accomplish here, and then we will download some code and we will fuzz it together. So I assume you're all aware of what fuzzing is, what the goal is, but I love this tweet. I think this exemplifies it perfectly. A QA engineer walks into a bar, orders a beer, orders 0 beers, orders 9 million beers, orders a lizard, orders -1 beers, orders a, however you pronounce these letters, right? So here we're fuzzing the bar. We're providing some input, hoping to find unexpected fault conditions. And yeah, this is what we might do with software as well. So let's talk about fuzzing strategies. Traditional dumb fuzzers just sort of mutated bytes randomly, one by one, hoping to switch a byte in a way that caused a crash. So you can imagine, like, if we have a PDF file, which is just full of random bytes here, if we go through and switch these up one by one, adding one, subtracting one, flipping the bits, changing integers from 0 to 1 to infinity, we might be able to find some crashes. And a great tool that did this from the past was FileFuzz. Has anybody used FileFuzz before? Remember that one? It's been a few years. This was a tool for Windows that you could give an executable you were trying to fuzz and give an input file, and it would just iterate byte by byte, changing those things, looking for crashes. Advantages and disadvantages. Advantages, it's really easy to set up and run. You just click a button, go. It's like a for loop just switching bytes. Disadvantages, you're not going to find many crashes using this technique. right? It's just not going to mutate files in a way that is interesting to the program. So a better strategy is what I would refer to as intelligent fuzzing, is to provide the fuzzer with some details about the structure of the input file. So rather than just saying, here is 1 megabyte of data, and I want you to flip bits until you find crashes, maybe we tell the fuzzer, hey, the first 4 bytes here indicate a version. And if that version number changes, the program isn't going to parse it at all, so just ignore those first bytes. And then the next set of 8 bytes is a traffic class. Maybe this is like an IPv6 packet. And the next set of 8 bytes is a traffic class, and that needs to be a specific number in order to reach some other code path. And maybe the payload length is something interesting to fuzz, but the source and destination addresses aren't. If we provide our fuzzer with some information about the file structure, it can be a lot more intelligent with where and how it mutates the input file to find crashes. Does that concept make sense? All right, just tell it like, this is a link. This is just data. Don't worry about this part, focus on these others. And there was a tool from the 2010s called Peachfuzz that let you input an XML file with your target program and your data file, and that XML file defined what your input data looked like. Anyone use Peachfuzz? Cool, okay, a few of us. Peach is a good fuzzer. But this still suffers from some problems that make it less likely to find some crashes. The problem here is code coverage. So let's imagine that we have a program like this with 4 if statements, and we're checking the first 4 bytes of the input file for A, followed by Z, followed by a $sign, followed by an X, and if and only if all of those conditions are met, are we going to reach this exploitable crash function, some faulting condition. In order to reach that, all 4 of these characters have to be in the right position. Is a dumb fuzzer, a traditional fuzzer, going to find that? I would say not a chance, never. Right? Just manipulating bytes one by one, even multiple simultaneously, there's a very low chance that you'll ever reach this bit of code. So would an intelligent fuzzer find this? If I told the intelligent fuzzer, hey, the first 4 bytes here are interesting characters, and I want you to switch those one by one, maybe they all have to be ASCII characters, there's a chance that we would find it, but it's kind of growing exponentially, right? Like the more conditions that have to be met to get there, the harder it's going to be to find. Each of those characters has 256 possibilities for a single byte, 256 to the 4th power, 4.2 billion iterations before you would find this crash. See what I mean there? So this is still a problem, code coverage. So how do we improve upon this then? How do we make our fuzzer more easily find code deeper and deeper in? So traditional fuzzers are not going to look at the majority of the code base, the majority of the branches, because they're never going to provide the right inputs to reach those code paths. We're guaranteed to miss bugs. So one of the strategies that we can use to solve this is something called guided fuzzing, or coverage guided fuzzing. The concept here is to track what the program does at runtime with our input sample and observe the path that it takes, save that coverage data, and feed that back into the fuzzer to give it some information about when it found a new path in the code. Right? So consider this little diagram here. We have our input corpus. These are all of the files, the data files that we're going to hand to the fuzzer to use to try and find crashes. We feed those through some sort of input mutation engine, and maybe it just changes single bytes, or we give it some intelligent data to work with about the file format. We stuff those into the executable that we're going to fuzz, and one of 2 things can happen. Either it can crash, wonderful, we found a potentially exploitable crash, or it doesn't crash and we get some coverage information about what path the program took for that specific input file. When I see a new path reached and I see it do something different, I take that input file and add it back to my corpus, so that now I've reached further down in the chain of potential events that need to take place, right? So this is a process, but this allows us to reach deeper into the program and find more complex code paths. So I think the seminal tool, the tool that really brought this to the masses and made this easy for everyone to do is AFL, which stands for American Fuzzy Lop, written by this gentleman who I think now works at Google. Anyone used AFL before? This tool is popular. It's slick. It's cool. AFL is great. That's what it looked like. This is kind of the old interface. It was published in 2015, and Michael, I think he worked on it for a few years and then kind of moved on to other things and abandoned it, but the community picked it up after and turned it into AFL++. So we still have a version actively maintained today, which I will show you here in a minute. So the way it works is we take the source code for the program that we're trying to fuzz, and before compiling it, we look through it and find every single branching statement. So an if statement is a branch, a loop would be a branch, a switch case would be a branch, calling a function is a branch, right? Anything that redirects the flow of execution to reach a different path is a branch in the program. And we compile the program using AFL and add a tiny bit of code at each of those branch locations that emits some information about, hey, I just reached a different branch. That way, when the program runs and all of these little bits of instrumentation are reporting what's happening, where the program is in its execution chain, we can sort of track when it does something new or something novel, something different. All right? So if I asked you then, with instrumentation, with those little bits of reporting on each of these if statements, would a coverage-guided fuzzer find this exploitable crash? The answer is almost instantly. Really, really fast. Because every time that I find the correct value for one of these bytes, I lock that in. I now have an input sample that's always going to start at the next one. Right? As soon as I see that this if statement did something different, I feed that sample back in, and now I'm working on the next byte. So I've taken a problem that was 256 to the fourth power, and I've reduced it to 256 plus 256 4 times. Vast speed increase. Instead of 4.2 billion possibilities, now I have 1,024. Way faster. Questions on that? Okay. So here are some modern coverage-guided fuzzers that you might want to look into if you're interested in doing fuzzing. AFL++, like I said, is the community-driven fork of the original AFL tool. It is way better. It's awesome. Every cool idea that somebody around the world had to add to this tool has been incorporated in. It's better than it's ever been. I'll show you how to use this one here today. There's another one called libfuzzer, which is part of the LLVM project. And I would say libfuzzer is more work to set up. You have to really do some manual intervention with the code that you're trying to fuzz to get it set up, but it's way faster when you do. So if you have the time to invest, libfuzzer is like AFL++, but better. There's another one called hongfuzz that uses what they call an evolutionary algorithm for their fuzzer. So it's coverage guided, but it's a little bit smarter about how it mutates those input samples. And it finds things that generate new paths and then combine those to, I don't know, do better than before. I have information in these slides about these two, but would definitely recommend looking into that one as well. Is that something anybody here has ever used or looked into? Okay. So,
One quick question.
yeah, sure.
Do you need the source code for the 3 of these?
It's a good question. For libfuzzer, well, actually, I'll answer this. The way that I'm going to show you how to do this, yes, you do. All of these you would need the source code for, because to add those little bits of instrumentation, you have to modify the program at compile time. But that's not the whole answer. It turns out, over the past few years, there have been methods developed to instrument a binary without compiling it, like just a black box binary, and these can be run against binaries without the source code now. I think actually Intel released a new technology with their new CPU generation. I forget what you call it. Intel released a way to have the processor detect a branching condition and report that, even if the code itself doesn't have that ability built in. Has anyone heard of that? I would have to Google the name. There are ways now. The way I'm going to show you, you do need source code though. I think it's more effective if you have source code. So let's set up AFL then. AFL is included in the Ubuntu repositories now. It's that popular, that good. They've just included it in the Ubuntu repos. If you are running a distribution that does not have AFL, or actually if you just want to run this on Windows, you can pull it down from GitHub and build it from source as well. But I think under Kali, you should be able to just do apt install AFL++. I have not tested that. So I'm going to hope, and if that doesn't work, we'll resort to compiling it from scratch. And if that doesn't work, I'll just show you, but I think it should work. Did it work? Wicked. You might need to run apt update first. So I'll tell you what, run these two commands. Run, let's see. Run sudo apt update. Make sure that you get a new list of available software. Sudo apt update. Type in your password. And then run sudo apt install AFL++, or you might even be able to just do AFL. I think they're aliases of each other. And with any luck, I already have it installed, but it should be available to you in the Kali repos. I'll give you just a moment to install that. Sounds like it worked for Logan. Did anyone else get that to work? 2 confirmations, 3. Sweet. If I can be of assistance, raise a hand. Okay, the way that we will know if this is installed and working is if you do AFL dash and then hit tab a couple of times, you should have lots of options, lots of different tools beginning with AFL. The two that we're going to use here today are AFL-CC, which is the AFL version of the C compiler. It's basically GCC with a little bit of code around it for that instrumentation. And then we're also going to use AFL-Fuzz, which is the fuzzing engine that observes a binary built using AFL-CC, watches all of those instrumentation details, and tracks the path of the binary, right? So we're going to use those two. There's lots of other good stuff in here you can go look at on your own. These are the ones that we want. So using AFL is pretty straightforward. We're just going to compile the software like we normally would using whatever build instructions the maintainers specify, but we're going to swap out our C compiler for AFL-CC. So this is a drop-in replacement for GCC or G++ or Clang or whatever you would normally use to compile. With most of the GNU tools, the build process involves running /configure and then make. Do those commands look familiar? Those things you've probably seen if you've built software from source before. So what we're going to do is either specify the compiler in environment variables when we run config, or specify them in variables as arguments to the make command. That's the idea here. So I'm going to give you a piece of software. We'll do that in just a minute. I'm going to give you a piece of software to fuzz, and let's build it together and see if we can find some crashes. So if you open up a web browser and you go to github.com/fuzz, /Ruzilla. That's my GitHub. Here, I'll paste that on the terminal so it's larger. That's my profile. I have a project called Crashy. So if you just go to that URL, go to github.com/Ruzilla/Crashy. Crashy is a program that does precisely what its name suggests. It crashes really well if you can find just the right input. This is one that I use in the reverse engineering class to kind of demonstrate this process to students, but I can show you with a real piece of software after this if you'd like also. So from that GitHub page, Ruzilla/Crashy, I'm going to click the code button here and select the URL. Let's just copy that. I assume everybody's familiar with cloning a GitHub project. Should be familiar. So I'm going to run git clone, and I'm going to provide it that URL. I'll zoom out just a little bit so you can see the whole thing. Git clone on that URL. And that should give you a new folder called Crashy. Within that folder, you will find source code, you'll find example input files, you'll find a make file to build it, and a README file. So, give you just a moment, make sure everybody was able to find that software and get it downloaded. Imagining this was a real software project that we wanted to fuzz, what do you suppose would be your first step to getting this thing built? What should we do? Probably, yeah, run make, or just check the README and see what that says. But it looks like we're going to be using make to build this program. If you want details on it, you can open up the README. There's build instructions, which indeed, look at that, you were correct. Crashy can be built by running make. So that will produce a binary called Crashy, which you can read up on your own. Basically, we provided an input file on the command line. It ingests that input file and does something interesting with it. So I'm going to run make, and that should give me, like the directions say, a new binary called Crashy. And if I look in the examples directory, there are some input example files that we can feed to the Crashy binary and let it read those and try to interpret them. So again, I'll pause and provide any assistance. All tracking, good. So let's test this with one of the example files then. Go ahead and run Crashy, so do /Crashy, and let's try it with examples/example1. So it looks like it printed, oh, you can't quite see. Let me move my window over. There we go. Looks like it printed an integer and a character and a string. Great. Pretty cool program, you might say. So we have our program built and working. Let's see if we can rebuild it using AFLCC so that we can fuzz it instead. Who can give me a command to run to build this with AFLCC instead of the defaults?
AFL-.
That would work, yeah, and provide it the input file. I think the easiest way, though, where did I have my slides? Let's just do this. And in fact, for this program, because it's all C code and not C++ code, I can ignore the CXX parameter on the end. That would only be relevant for C++ code. So I'm just going to run make, and I'm going to tell it the C compiler that I'd like you to use is AFL-CC. And what we should see is that when we run make, we should get some output, AFL-C, C++, instrumented some number of locations. That's going to tell you that it's working as expected. So I'm going to run make cc equals AFL-CC. Ah, much better. There we go. So I can tell that it worked because I see it instrumented 30 locations. The binary should still run and work as usual, right? Crashy.bin, example/example1 still works, but it's reporting some extra coverage information also as it runs. So how do we fuzz this then? So the tool that we're going to use for fuzzing is AFL-fuzz, and really you only need to know about 2 command line arguments to get it going. It has lots more than that. I'd encourage you to look through them on your own. The 2 that you need to know about are tick-I for the input directory and tick-O for the output directory. Input directory is your data files that you're going to be feeding the fuzzer for it to use to try and crash the program. Output directory is where it's going to store all of the information while it's working on that binary. So that's the fuzz queue, right? As it's collecting new samples from the coverage information, it's going to store them there. Also crashes, also hangs. So if the program just stops, doesn't run any further, it'll store an example of that in the output directory. And then following that, the syntax is you just add the program as if you were running it normally and use the term et as a replacement for where you want your input file name to be provided. By default, fuzz input is going to be provided on standard in, but in our case, since we're providing it an input file name instead, we're going to use et. So we have our binary instrumented. I already have an input directory. I have all of those example files that I can use as inputs. So I probably need to create an output directory then, right? So I'm just going to do mkdir output. Now I should have a new directory called output here. Okay. Now I'm going to zoom out just a little bit so this all fits on the screen. And I'm going to run AFL-fuzz, tick-I, examples, tick-O, output, and then I'm going to provide it crashy.bin et. And if you want to be clear where AFL's command line parameters begin or end and the other programs begin, you can put a dash between. I don't think that's going to be explicitly necessary here, but sometimes it might depending on how complex that command line string gets. That just separates the 2, right? So when I run this, depending on how your computer is configured, it may just start going or it may throw an error. Did anybody get an error? Something about some did, some didn't? I hope that mine throws the error so I can show you how to solve it. There we go, perfect. This is expected. AFL needs you to change some of the settings for your kernel in order to see crashes as they occur. So we're going to just follow the instructions here. Basically, it's as easy as switching to the root account and running this one command. This is not something that I would run on your own personal laptop regularly because, it changes how crashes are reported. And so if you have a daemon monitoring for crashes, now maybe it doesn't see them and AFL does instead. Probably you want to do this in a VM. This is not for your everyday driver machine, but I'll go ahead and run it on my computer. Now I'm going to switch to root and change how crashes are reported. So copy that command, switch to root, run that command, exit out, and now when I run this, there's a chance that I'm going to get one more error. There's one more thing that I might need to fix. We'll see. Yep, okay. So my CPU frequency scaling is not in its ideal setting for AFL. So again, we're going to switch to the root account, and this time I'm going to run these 2 commands, which I think, I'd have to read again, I think it just disables CPU frequency scaling. So it keeps the CPU running in a more predictable way. So again, let's switch to root, sudo tick-I. Tell me to slow down also if I'm...
We did get an error on our side.
Oh, yours is just running.
Yeah.
Who else is just running?
I just
Wow, all right. I'm the one who's behind. All right, so I'm going to switch to root. I'll just move faster here. So I assume you already have crashes and everything?
Yeah.
Wicked. Amazing. Okay, well, please hold. Apologies. My computer is not in its optimal form for fuzzing at the moment. Lesson is, if you see those errors, just switch to root and run those commands. Now I'm going to run this one more time, and now I should see what you see. Oh, my terminal's too small. There we go. Okay, so I'm going to let this run for a minute. Corpus count is how many new paths the program found, how many new branching conditions. We can see what techniques it's using to try to mutate the input samples over here. More information, you could read up on AFL to see what that does. But now I'm just going to wait and see if I can find any crashes. Who has found crashes so far? About half of us. Excellent.
So what's a havoc and a slice?
Okay, so I'm going to do my best to remember what those do. Might be a read the manual situation. Havoc, I think, just randomly picks bytes throughout the file and changes them. Slice, I think, you know what, I don't know.
It's a change in the code.
Yes. Yep. Bit flips is obvious, byte flips, known arithmetics is like -1, int max, int min. I would have to look and see what splice is. I'm not sure.
It's modifying the input file,
Correct.
not the code.
Correct. Yeah. Yeah, so we compiled the code into a binary that reports coverage information, but it's modifying the input files. Wow, and look at that. It found some crashes. We got it. Is anybody here still waiting on crashes? Hasn't happened yet? So there's some randomness to this, right? Like, some are going to go faster than others. It's also interesting to see AFL has detected 6 crashing files, but it only saved 3 of them, probably because it noticed that 2 of them, although different, reach the same crash in the same path. Right, I got there in the same way. I'm guessing that all 3 of those are still the same root cause. We just got there in a different enough path that AFL couldn't tell, but it's trying to deduplicate those as best that it can. I'll give this just another minute. I want to make sure everybody has crashes before we go any further. Yes, sir.
So clearly, the default is for it to kind of fuzz full bytes. Are there ways if you know the input is ASCII specifically, why not for you to say, oh, only try these characters?
Yeah, so one of the ways that you can speed AFL up in that case, actually, I'm going to go ahead and just kill my fuzzer here. If you found crashes, you can kill the fuzzer. That's all we need. If not, let it run another minute. But if we run AFL fuzz -- help, there is an option for dictionary file right here. So let's say we're fuzzing like an HTML parser or a JavaScript engine, something that's not just, raw binary information. I might provide it a dictionary of input words, var, function, HTML, body, a, source, href, and I can tell the fuzzer, use these mean something specific to it. I don't think that fully answers your question because it doesn't fully restrict it to only those things, but at least that provides it some additional information. That has been highly effective for me in the past. Like that really speeds up the process. Find crashes that you otherwise wouldn't get. It's a really good question.
So this is very similar to cracking passwords.
Yeah, I mean, there's something thematically similar in that we're just using all of our CPU power to try and brute force the answer to a problem. There's nothing real, cerebral here from a reverse engineering perspective. We're not reading through and finding the flaw, but we're kind of brute forcing our way through it. Yeah, so thematically similar. So I want to show you one more cool thing that AFL can do, and then depending on how much time we have 25 minutes left. So I'm going to show you one more thing, and then we might just give you the rest of the time to play around with this and do CTF. And
Are you going to show us the crashes and what's suspicious?
absolutely, yes. And I'm going to show you how to get to the root cause a little bit quicker too. So if I look in my output directory, there should be a folder there called default, and within that default folder, there should be a folder called crashes. The naming scheme that AFL uses is arduous at best. It's a little bit tricky to understand what these files mean. So I'll try and break it down. The first number here is just a sequential number as we get more crashes. The next number is the signal that was generated. So I think that signal 6 is abort, which probably means there was a heap overflow, underflow, some sort of heap corruption, and libc bailed out. Signal 11 is a segmentation fault. So either of these could be related to memory corruption, but it just crashed in a different way. After that, we have information about when the crash occurred. We have information about the type of technique that was used to find it. And I think also one of these numbers, maybe source, is an indication about which input file from the corpus was modified to produce that crash. So I'm not going to attempt to parse everything going on here, but this really complicated file name has some indication of how we reached that crashing condition. So it helps you work backwards. So we still have a problem though. If I open this thing up, it is 68 bytes. 68 bytes is not a lot, but it's going to be a lot for us to work through in 20 minutes here. So I'm going to show you how to pare that down a little bit. I'm going to, let's see, I'm going to hex dump dash uppercase C, the output slash default slash crashes slash ID 00. So I'm just going to hex dump the first one and see what's inside. Okay, bunch of stuff. I have no idea just from looking at that how and why the crash is occurring. Now maybe a good first step would be to run it in GDB and try and figure out what function is causing the crash, where the crash is occurring. We could probably work our way towards the answer there. But I'm going to guess that a lot of the data in this crashing file is not actually important to the crash itself. Like probably of these 68 bytes, only 10 or 20 of them are actually needed in order to reach that crashing condition. Probably a lot of the bloat here and the extra junk that's added in is just stuff that the fuzzer was adding as it was mutating, reaching the point where the first crash occurred. So I'm going to use another tool included with AFL called AFL tmin, which is the AFL test case minimizer. And I'm going to use it to try to minimize this crashing sample down to the smallest possible form. So what it's going to do is it's going to chop this file up into lots of little pieces, and it's just going to try removing little bits at a time. So if I remove these 2 bytes, does it still crash? What if I remove those 2 bytes? What if I remove those 2 bytes? And eventually it's going to remove enough that it no longer crashes. Okay, stop. Now include those last 2 bytes. Now go through all of those bytes. Can I change them to just a capital A or a 0? Does it still crash? Does it still crash? And it's trying to minimize the data in here as much as possible to make it easier to reach the answer. So AFL tmin works basically the same as AFL fuzz. We're going to give it an input file in this case, not a whole directory. So the input file is output, default, crashes, ID 0. Tab is your friend there if that's not clear. Tab completion. Please don't type all that out. Or do. You'll be here a long time. And then -O is going to be where we store the minimized file. So I'm going to call this one id0.min. I'm just making up a name. Doesn't actually matter. And then just like when we fuzzed it, I'm going to provide the program, and I'm going to provide @, where the file name should appear, and it's going to repeatedly run that file back through the program, trying to shrink it down as much as it possibly can. Does that make sense? There's some fancy algorithms there. Let's see how good it does. So, in my case, given my random crashing sample, it was able to reduce 36, oh no, more than 36. It reduced 47% of the file, so it reduced it to 36 bytes from, what was it, 68? So we reduced it almost by half. Let's take a look at both of those files then, the original and the new one. So there's the original. Let's take a look at the new one. Let's see what they look like. Much simpler, right? Smaller and less noise. The one up at the top has all sorts of random bytes at the end and just hard to visually parse. This one is smaller, and although it appears there's some random bytes at the beginning, most of the data after that is just hex 30, just a 0. So it shrunk it down as much as it could, and then it eliminated the complexity from those bytes as much as it could. And now I have a nice, clean crashing sample. So we have 20 minutes left. I have a challenge for you. Open up crashy.c and see if you can figure out where and why this program or this input file crashed the program. Or if that sounds difficult, CTF is fine too. But I would love to see if somebody can figure out why this particular sample crashes the program. Right? So I guess I could take questions as well. Mike, I'm sure, would be happy to take questions. We can spend the last 20 minutes talking about AFL. I could show you libfuzzer, try and find the crashes. What are y'all in the mood for? What's that? Blackjack. Fair. Fair.
So how would you use this or would you use this in malware reverse engineering?
So I would say this is less focused on malware. This is more focused on software exploitation.
Okay.
Right? This is sort of it's related to reverse engineering, right? We're not doing reverse engineering directly, but this is a tool that I would use to get me a little bit closer to the specific area of the code that I want to reverse engineer to find a problem. So one of the reasons that you might want to do RE work is to find crashes, find vulnerabilities, write exploits, and this is going to help you find where in that code base to go. If I try and do source code review on a JavaScript engine, that's hundreds of thousands of lines of code. But if I can fuzz it and see that one particular function is crashing, then I can go right to that. So yeah, maybe I should have made that clear before just kicking it off right at the beginning. What we're doing here is related to reverse engineering, helpful in the reverse engineering process, but not so much for malware analysis, more so for software exploitation.
Unless you're trying to exploit the malware.
Which is also something that folks do.
So have you done any fuzzing on anything besides crashing in your career?
Oh yes, certainly.
So give us some examples of things that you fuzzed?
So I found some crashes in the PHP interpreter using AFL, basically just like this, compile it and run it over a series of several days, and wrote some exploits for those. If you want to see some of that work, actually the work that I published is not AFL related. I wrote a custom fuzzer for that. Check out, what is it, blog.jmpesp.org. I'll make that URL larger. This is not directly using AFL, but I did the same thing with AFL. I have some write-ups here on finding crashes in the PHP interpreter. I made up this module on fuzzing for my reverse engineering class this past summer and actually found some crashes in the NASM assembler as well as in GDB. There's more of those to find as well. So I could show you some of those if you want, but yeah, you can definitely
So
find
did
them.
any of that lead to an exploit?
Yes. Well, not for NASM, for the PHP interpreter. Yes, it did. And I don't think that I actually published that
I was
exploit.
saying, did it lead to a vulnerability being discovered?
Yes. Yeah. So in
You didn't create an exploit, I assume.
Oh, I did write an exploit for it, yes. Oh, yes, and I could show you that as well if you want. It's for an older version of PHP, so I might have to do a little bit of setup to get it working. But I used another tool, Damato, to do some context-free grammar fuzzing against the PHP interpreter. And long story short, if you read the blog post, the crash here was a use after free in the XML library, XML reader and writer. So it was something to do with when you opened an XML file, it would create a structure to manage the file handle to that thing on disk. And when you did start comment, let's see, how does this work? You could force it to double free the memory that held the structure for the handle to the file on disk. So you could force it to free the handle and then force it to free it a second time, but have overwritten that memory in the meantime. And when it freed the file handle, it would execute a file pointer to try to flush the data out to the terminal, which you could then hijack to get code execution. To just put it very concisely. Let me see if I can find that exploit.
Did you notify the PHP?
Oh yes, it's fixed. Yeah, if you look at bug 79029, here's the bug report, here's the examples. So basically, you create a new XML writer object, open nothing, you close its file handle, and then when the script exits, it got closed a second time, which did a double free. I reported that to them, they got it fixed. It was a one-line fix, that was easy. Let me see if I can find
So what did they pay you?
a little bit of money for that one. There was a bug bounty for that one. Yeah, it can be a lucrative business.
Yeah, S corp.
What's that?
It's an S corp.
Yeah, it's good stuff. What did I call that code?
Maybe that challenge based off too, that CTF challenge.
Did I off of that one?
Just based on the, because it's a 2-byte shellcode, wasn't it?
Oh yeah. So also, if you go to ctf.hostbin.org, there is a shellcode challenge here, which is based off a problem that I encountered while I was writing that exploit. Yeah.
So how much time did you invest in finding that?
Several days, couple of weekends of work. A good amount.
Was that mostly waiting for the fuzzer?
It was a lot of, well, so in this case, I wasn't actually using AFL. Where did here we go. In this case, I was doing grammar fuzzing. So basically, I defined the whole PHP grammar to the point where I could tell it, generate an expression. And an expression is composed of, some number of variables and operators followed by a semicolon. And a variable is structured this way. And then I defined the grammar in a way that my fuzzer could just generate lots of these. And it eventually happened upon this particular crashing example just from randomly spitting out syntactically correct PHP code, which then crashed the parser.
So you could go back to the grammar that you defined and find those 6 lines?
Yeah, so let's see. It's been a little while since I went through all this, so forgive me. Basically, I defined the grammar like this. So a fuzz bool is a true or a false. A fuzz integer is a fuzz int. A fuzz int is a 0, 1, a -1, a million, a large integer or a negative large integer. A large integer is these things. A float is this thing. A string is a string repeat. And I defined, a variety of different components, which then, when put together, produce what looks like this. This is what it ultimately looked like. Have all these objects instantiated in memory for it to interact with, and then it just has a whole bunch of try catch or try accept, and they do random stuff. So this one takes vars SPL priority queue and executes the insert function with parameters of false and an array. This one executes filter has var 1000 with string repeat, hex 100. Just does a whole bunch of random stuff.
So that was what Omado was generating?
Yes,
Okay.
correct. Yeah, this was the output. And it would spit those out, 1,000 times a second. And then I had lots of different fuzz nodes that I was sending samples to test. And then it would report back if there was a crash.
And the fuzz node is a Omado instance that takes that.
Yeah,
Okay.
Yeah, basically. God, I forgot where I stored those files, but I think the file had a name kind of like this. Is it one of these? Dakotacon. Ah, yeah, here we go. 1-exploit.php. Okay, I'll see if I can show you kind of how the exploit worked. Extra Cheese has a cheesy ASLR bypass. I think it's this one. Yeah, okay, here we go. So I'll do my best to walk through this. Okay, this is a cheesy way to bypass ASLR, but it proved the point. I have some shellcode there. So what the program did is it created a file on disk, created a new XML reader object, used the XML reader object to open that file, and then it closed the structure containing the file handle for that file on disk. So from the XML reader object's perspective, it still has a file open, but in actuality, that structure has been destroyed and that memory has been freed. Then I allocate a very precise amount of memory, which occupies exactly the same space as that thing that just got freed. So I don't know, what's our familiarity level with like heap memory allocation, malloc and free? Familiar with those functions? So on many Linux systems, if you free a block of memory and then allocate a block of memory of exactly the same size, the memory allocator will put it in the same place because that's just the most efficient block of memory to allocate. So if I free that block of memory and then allocate something of the same size, I occupy that memory space, all right? Then we do a cheesy ASLR bypass because I didn't want to find another bug to accomplish that. And then, let's see, we say we found the object. So this is kind of, here's a whole other story. I figured out that you can get executable code in memory on a JIT compiled regular expression page. That's a whole other story. Basically, we put shellcode in memory and then use the cheesy ASLR bypass to find the address of that shellcode, and then build a fake object that looks like the object that was freed, such that one of the function pointers in that object points to our shellcode in memory. So this is a function pointer for a filter whose file operations filter is used to like flush the data out to the screen right before the program exits. So if I overwrite the file handle object with an object that contains a pointer to my shellcode instead of the function that should be used to flush the output, then when I free the object a second time, so we overwrite the object, trigger the use after free, which frees it a second time. Yeah. When it exits and tries to flush the output stream, it ends up executing the shellcode address instead. We're going off a big tangent here, but it worked well. It worked. So anyway, I didn't mean to completely redirect everything to that, but this is kind of where reverse engineering can ultimately take you, I guess. Ultimately get you.
So in your just to bring it back.
Yeah.
So in your crashy code, I can't kind of figure out how do you go from the the file in the examples directory
Right.
to what your crashy code takes as input.
So
So I see that in the main you use RxC and RB for some page statements.
So you're asking, like, what would be the process of taking this crash now and tracking down why it's crashing? Where is the vulnerability?
So, yeah, I mean, more of like, so if we got into the internals of AFL,
Uh-huh.
how does it give these as input to your crashy dot?
Oh, yeah, okay. So AFL does something cool. It has what it calls a fork server. So if a program forks, we create 2 copies of the same program, right? So AFL will start up the program, get it right to the point where main is about to execute, and then pause execution. And then it will continuously fork off processes of, like clones of itself. And it will use, I think, symlinks in the background to point that file name to a different sample every time, so that for each program that it forks off, each of those tests something else. And that speeds up the process a lot because you don't have to completely build and destroy a new process every time. You're just forking off existing processes, and then via those links, tests different.
So then eventually one of those links leads to a crash, right?
Yes, leads to a crashing sample.
So then it records the input that it gave to that link, which then
Right.
led to the crash. So then that input that it gave to that link to crash, how do you determine?
So AFL watches the signals that the program throws. When a program crashes, it's a segmentation fault, right? What that actually is, if we look at man7 signal, I think this is the file. Maybe, yeah, here we go. What a segmentation fault actually is the program exiting with signal 11. Like, if a segmentation fault occurs and the operating system says you accessed memory that you shouldn't be allowed to touch, raises a segmentation fault, sig v, the program exits. So the AFL fuzz program, as it's spinning off all of these cloned processes, is monitoring for what signals they exit with. If it exits with like 0, success, we just ignore it. Throw that sample away, it wasn't useful. If it exits with signal 11, or I think I saw another one that was signal 6, sig abort. Sig abort can be interesting because libc will generate sig abort if there's memory corruption it detects. So that might be something to look at as well. That the AFL fork server is monitoring all of those child processes and checking what signal they exit with.
Gotcha. What I meant is more like it spins off that link, right? That link, you have to give main a particular input.
Right.
And that particular input is your answer, finally the answer, right? That goes into the output you're returning.
Somewhat, yeah. But it's mutating those input files.
But you record the one that took you to the sig abort.
Yes.
And
Yes.
that's ultimately what you want, right?
Yes.
That's the ultimate. Yeah, I'm just having trouble kind of like looking at those bytes and just figuring out where to start to translate that into
So
that input.
I'll do my best to explain this fast. We're almost out of time, and I don't want to. The blackjack tables are calling, I'm sure, so I don't want to hold everyone longer than you need. But I think if I was working on a real program here, what I would do is I would start up Crashy in GDB, right? And I would run it with that particular input sample as an argument, and I'd watch it crash. Okay, it crashed. So it stopped here, right? We got a segmentation fault, or no, maybe we didn't. Was this our sig abort? Oh yeah, okay. This is a bad example because we got sig abort. Probably I'd want to use one of the segmentation faults. And then I would check backtrace and see, how did I get here? So we ran main from within Crashy. Main ran parse. Parse ran printf. Printf did a whole bunch of other stuff. And somewhere inside the printf function, libc noticed that something was wrong with the heap and went, oh my God, we got to exit. Something bad happened. And usually when that occurs, that means that the corruption actually happened a few function calls earlier, right? It's crashing because it noticed a problem after the fact. But that backtrace would at least allow me to start to work my way backwards through the code and find what went wrong.
Okay, yeah. I thought it was like you could look at the I thought there were fewer steps between.
I would say from there, it's working. That's where the reverse engineering comes in. So with that, thank you everyone.
Yeah, thank you.
Sorry, I went off the rails.